In 5.7, we're going to learn more about the zeros of polynomials. The biggest theorem we're going to talk about is the fundamental theorem of algebra. So we'll talk about that first. We're also going to talk about the complex and irrational conjugate theorems. That will actually, the fundamental theorem will also mean I want to talk about multiplicity for our zeros, what that is and what that means as far as interpreting a graph. And then the last thing, we're going to use the information we have to write a polynomial given its zeros. So we've spent the last few sections taking a polynomial and finding its factors in order to find its zeros. So we're going to do that backwards. That's the last thing we'll do in this lesson. So the fundamental theorem of algebra is actually pretty simple at its core. What it says is that if you have a polynomial and you can find the degree of that polynomial, the number of zeros for that polynomial is based on the degree of the polynomial itself. So here for my first example, x cubed plus 7x squared plus 15x plus 9. That's a third degree polynomial. So the fundamental theorem of algebra, the basic part of it, says this has at least one solution in the complex number system. The corollary actually specifies this one has exactly 3 solutions if you're willing to count the same solution multiple times or to count complex solutions. So we're gonna break that down a little bit. This one actually has the same solution more than once, so I'm going to show you what that looks like. Now, since we've already done synthetic division, that's going to come into play this lesson. But the first thing I'm going to do when I approach a new polynomial and I'm going to break it down is take a look at the graph, because that's going to tell me which zeros I should be looking for. So let me bring up my Desmos graphing calculator here, and I'll type in the polynomial x cubed plus 7x squared plus 15x plus 9. And I can see from the graph here that -3 is a good number to check, as is -1. So that's where I'm going to start, is -3 and -1. So first I'm going to use -3, and I'm going to use synthetic division to start breaking down my polynomial. 1, 7, 15, 9. So that's 1, -3, 4, -12, 3, -9, 0, as expected. I could use synthetic division again, but this is already quadratic, so I should be able to just factor it. So I have x plus 3, that was what I divided by here. This one, I'm expecting it to have a -1, which means x plus 1 should be one of the factors, and it is in fact. The other one is x plus 3. That's what makes adds to 4 and multiplies to 3. But you'll note here I have actually x plus 3 twice. And this is what we call a repeated solution. So we can rewrite it as x plus 3 squared times x plus 1. So this polynomial has, if you're willing to count repeated solutions, it has 3 solutions. It's just the solutions are -3, -3, and -1. We normally wouldn't count this as 3 solutions. And that's why the basic fundamental theorem of calculus says it can have up to 3 solutions. If you're willing to count the complex ones and you're willing to count the repeated ones multiple times, then you're going to find there's exactly 3. And that's useful for knowing when you're done, because each factor represents a solution, and each one is represented by the degree, or the number of them is represented by the degree. So as you break down a polynomial, you can know you found them all, and that way you don't have to worry about ones that you might have missed. So this is called a repeated solution, which means it has a multiplicity bigger than 1. And we're going to get to that when we talk about multiplicity. But there's the fundamental theorem of algebra for you. It tells you how many solutions you'll have, although you have to be careful to understand what you mean by that as far as how you count them. The conjugate theorems say that when you're looking for solutions, if you have a polynomial that has rational coefficients, there's no i's and there's no square roots in the original polynomial, then if one of your solutions has a square root in it, or one of your solutions has an I in it, which is really just a kind of square root, then if it has that, it also has that number's opposite. So we write our imaginary numbers, hopefully you remember from chapter 4, a plus bi, and the conjugate for an imaginary number has the same sign in front, but the opposite sign in front of the imaginary part. It's called a complex conjugate. And what the complex conjugate theorem says is if a plus bi is one of the solutions to your polynomial, then its conjugate is also one of the solutions. And it works the same way for square roots. If the square root of b is irrational and a plus the square root of b is a solution, then a minus the square root of b is a solution. If you prefer your examples with numbers, if you have, say, 3i as a solution, in that case a is 0, it's 0 plus 3i. 0 minus 3i is also a solution. Or if you had 1 plus i, 1 minus I is also a solution. Or if you had 2 minus 4i, then 2 plus 4i, also a solution. Works the same with square roots. If the square root of 2 is one of your solutions, and there's no square roots in your polynomial, then negative square root of 2 will also be a solution. Similarly, if you have 1 minus the square root of 5, you'll also have 1 plus the square root of 5. So those are conjugate pairs, and as long as what you have is a square root as one of your solutions, either I, a square root of a negative, or just a square root of not a perfect square, its conjugate will also be one of your solutions. That's the complex or irrational conjugate theorem. It says they always come in pairs, which can be very helpful for when you're trying to track them down. It also means that when you get to the end and you have your quadratic, if you're having trouble factoring that, you should think about the quadratic formula, because it's the best way to figure out if you have imaginary or irrational solutions. So it's the complex and irrational conjugate theorems, just says they come in pairs. As far as multiplicity, we should talk briefly about this situation. When you have a repeated 0, it actually changes the way the graph looks. And we can actually see that if I go back to the graph I made here. There's a difference between the way the graph looks over here at where x equals -1, it comes right through. It's pretty straight as it comes right through. Whereas over here at the -3, you can see it comes up to the axis, but it moves back away. And that's typical behavior for something that has an even multiplicity. Since the -3 is a 0 twice, it's going to produce a place where the graph comes up to the axis and reaches 0, but then doesn't actually cross over it. It comes back off the same way, so it bounces off the axis rather than crossing. We'll see a similar behavior if we have for any even multiplicity. So if I change this to x plus 3 times x plus 1, you can see in this case they both have multiplicity 1, so at both zeros we're going to cross the axis. Now what we had on our original graph was multiplicity 2 for this one, and you can see the first one crosses and the second one, the first one bounces and the second one crosses. If I make them both squared, they're both going to bounce. Now if I make this one third degree, that's odd, so that produces a situation where it crosses the axis. This one is still even, so it bounces. So zeros with even multiplicity will bounce off the axis. Zeros with odd multiplicity will cross the axis. So that's going to give you information. If you're looking at a graph, you can predict the multiplicity of a given 0. If you know the multiplicity of a 0, you can predict the behavior of the graph. It works both ways. And that's why it's a useful concept. As far as actually making use of this, I'm going to go to my next example. X to the 5th minus 2x to the 4th plus 8x squared minus 13x plus 6. So this polynomial is 5th degree, so I'm expecting it to have 5 solutions. Some of them may be repeated and some of them may be complex. So the first thing I'm going to do is take a look at the graph. All right. So let me type that in then. X to the 5th minus 2x to the fourth plus 8x squared minus 13x plus 6. So in the graph here, I can see there's a 0 here at -2. So that's something I want to look at first. There's a 0 at +1. This bounces off the axis. So it has an even multiplicity. It occurs either twice or 4 times. My total needs to be 5. This only accounts for 3 of them, unless this is actually 4, but it looks squared to me. So we'll take a look at it when we get there. But that only accounts for 3. I'm predicting or expecting there'll be 2 complex solutions as well. The only way for me to find those is going to be the quadratic formula. So let's go take a look. So as I said, -2, we're expecting that to have a multiplicity of 1. I'll do it first. 1, 5, 4. Oh, there's no x cubed, so I need to make sure to put in a 0. 3, 8x squared, -13x, and 6. So 1, that becomes -2, adds to -4. Multiply gives me +8. So this is 8, -16, -8, +16 is 3, -6, 0, as expected. Now I also said +1. So I'm going to do that. Make sure you do that to the quotient, because each time you're breaking the polynomial down a little bit more. -3, 5, 5, -3, -3, 0. 1 had a multiplicity of at least 2, so I'm going to use it again. 1, 1, -2, -2, 3, 3, 0. So I've got x plus 2. That was the first thing I divided by. I divided by x minus 1 twice, and what I have left is x squared minus 2x plus 3. At first you might think that's -2 and +1, except that would produce a -3, whereas this is a +3. They'd need to be the same sign, 3 and 1, and they'd add up to 4. So this is not going to factor nicely. I'm going to need the quadratic formula. So yeah, the 1 has a multiplicity of 2. These are going to be imaginary solutions. So I'll use the quadratic formula. It says x is equal to the opposite of b, plus or minus the square root of b squared, minus 4 times a times c, all over 2a. So that's 2 plus or minus the square root. 4 minus 12 is -8, all over 2. That's I. 8 is 2 times 4. The square root of 4 is 2. There's the square root of 2 in the square root of 2 left behind. So the 2's all cancel. I get 1 plus I times the square root of 2. Oh, plus or minus. So that's my last 2 solutions. My solutions are -2, +1 twice, 1 plus I square roots of 2, and 1 minus I square roots of 2, which 1, 2, 3, 4, 5 is 5 zeros as predicted. So I used the shape of the graph to predict the multiplicity of one of my zeros, which was helpful because I knew exactly what to divide by. The last thing we want to talk about then is writing polynomials from a list of zeros. I'm going to do this twice. No, I'm going to do it once. My video is already running a bit long. So I'm going to write a polynomial which has a given list of zeros. 1, 2, and -2 minus 5i. Now, if I want my polynomial to have real coefficients, if -2 minus 5i is one of my zeros, its conjugate has to also be one of my zeros. So I have to add -2 plus 5i to my list, which means I'm going to have 4 zeros. I'm expecting to end up with a 4th degree polynomial. Now, each one of these zeros corresponds to a factor. The first one then, x minus 1, because 1 is one of my zeros. Because 2 is one of my zeros, I get x minus 2. x minus negative 2 minus 5i, and x minus negative 2 plus 5i. In order to turn this into standard form, we're going to need to multiply all these together. I'm going to multiply the complex ones first because I guarantee, since these are conjugates, when you multiply these, the i's are going to cancel. We learned to do that in chapter 4. Don't let it intimidate you. So I'm going to distribute this negative sign to make things easier. That's x plus 2 plus 5i, and x plus 2 minus 5i. And I'm going to put one on top of the other. And then multiply them together. So 5i times negative 5i is negative 25i squared. But I squared is negative 1. So that's going to make this positive 25. That's the constant column then. 5i times 2 is 10i. 5i times x is 5xi. Those are both imaginary, but they're going to cancel out by the time we're done. When I multiply the 2 through, I get 2 times negative 5i, which is negative 10i. See, that's going to cancel. 2 times 2 is 4, which is like terms with this 25 over here. So I'm going to put it over here in this column. 2 times x is 2x, which needs a new column. Then I multiply the x through. X times negative 5i is negative 5xi, which is going to cancel there. So see, all my i's are canceling out. X times 2 is 2x again. And x times x is x squared. So when I add all this up, I get x squared and 4x. Those are going to cancel, and 29. I still need to multiply x minus 2 and x minus 1, so I'll do those next. When I multiply x minus 2 here, 2 times 29, negative 2 times 29 is negative 58. That's negative 8x. That's negative 2x squared. Then I get 29x, which goes here in my x column. 4x squared and x cubed. So x cubed plus 2x squared plus 21x minus 58. And then I multiply by x minus 1. So when I multiply negative 1 through, I'm going to get positive 58, negative 21x, negative 2x squared, and negative x cubed. When I multiply the x through, I'll get negative 58x, positive 21x squared, 2x cubed, positive 2x cubed, and x to the 4th, which shouldn't surprise anybody because I said right at the beginning this was going to be a 4th degree polynomial. Negative x cubed plus 2x cubed is x cubed. That's 19x squared. That's negative 79x and positive 58. Oh, sorry. Just added the like terms there. So here I took my polynomials. Make sure you find the complex or irrational conjugates if you need them. For each one, then you get a 0, or each 0 you get a factor. You multiply the factors together. There you have a polynomial in standard form. Good luck.